So another component of a circle is something called the arc length, which is the distance between 2 points along a section of a curve. So I want you to think about a circle over here, and we'll kind of expand this so you can see it better. And from the center of the circle, okay, and this would be the radius from the center to the outside. Let's say we were to cut a piece of this circle. The distance created from the terminal arm of that piece, this section over here, with respect to the radius, that would be some kind of angle. Now, the arc length refers to this section here. That imagine we were to take that curve and flatten it out. Okay, so this here, if you flatten the line, what distance or length would you have? Okay. And that distance or length that you would find would be called the arc length. So one pattern that is consistent with the arc length is that the ratio between the arc length and the circumference of the circle, so a full rotation here like in orange, okay, is equal to the ratio of the principal angle and one full rotation, 360 degrees. And of course the principal angle would refer to that theta value right there. So let's say we want to know what the circumference of the circle is if the radius is 4 centimeters. So if we were to calculate that, we'd go C is equal to 2 pi r. In this case, it's 2 pi 4. And we were to keep it in radians, just give exact values. We could say that it is a value of 8 pi, right? Because 2 times 4 gives you 8 pi. And this, of course, would be the full circumference, which comprises of 4 arcs. So then imagine we have a 90-degree angle. So I'm going to write 90 degrees. That would go from here to here, basically. So how much would one arc be? Well, it's safe to say that if we have 4 arcs being 8 pi, right, then 90 degrees, which would be 1 arc, you're basically taking that 8 pi and you're dividing it by 4. So if I go 8 pi divided by 4, then I can assume that the arc length is going to be the length of about 2 pi. So I'm going to draw an arrow here that says 2 pi. Now I'm going to show you something. So that's the arc length compared to the circumference, right? So if we go arc length ratio to circumference, we can see that that gives 2 pi to 8 pi. And we were to simplify this, that is basically 1 to 4. Now, if I go, if I look at what the angle would be, the principal angle, which in this case is 90 degrees, right? So just like this. And if I take 90 degrees and I put it up against the full rotation of 360 degrees, I would see that this would also be 1/4 after simplifying. So the ratio between the arc length and the circumference of the circle should always be equal to the ratio between the principal angle, in some cases we call this the central angle, and 1 full rotation of 360 degrees. So now applying this same logic, what is the arc length of angle 60 degrees? Well, I've drawn it over here. It's shaded in pink, so 60 degrees. Now in comparison to the 90 degrees, I can see that it's going to be less. So I'm talking about the arc length of 60. Now it's only this portion here as opposed to the entire yellow portion. So what is that curved value if I were to straighten it out? Well, again, let's look at what the ratio between the two angles would be. So if I go 60 degrees over 90 degrees, right, that would be a 2 to 3 ratio. So what I could do is I could take that, I could go 2 over 3 multiplied by the arc length that 90 degrees was, which was 2 pi, since it's only going to be 2/3 of that arc length. And then what I see is that I end up getting about 4 pi over 3 as my arc length. Now, does this make sense if I compare the two ratios? So let's say I take the arc length and compare it to the circumference. So if I go 4 pi over 3 divided by 8 pi. This breaks down into 4 pi over 24 pi, which then can break down, if I divide 4 into 24, that could break down into 1 over 6. Okay, is the ratio between the arc length and the circumference. Now, if I take the angle, which was 60 degrees, and I divide it by 360 degrees, I would see that after simplification, it is also 1 over 6. Hence, we've proved that the relationship between the principal angle and a full rotation is always going to equal to the relationship, or the ratio, I should say, between the arc length and the circumference of a circle. Okay, so now expressed as a formula, we could say that the ratio of the arc length, so A, over the circumference of the circle, so we could say that's 2 pi r, is going to equal to the principal angle over 360 degrees. Now, if we write this in radians, which is, arc length over the circumference 2 pi r is equal to theta, that principal angle, over 360 degrees in radians, which is 2 pi. If we simplify this, so if I isolate for A and I multiply this entire side by 2 pi r, then we would see that the pi's would cancel out, and ultimately your working formula, especially in this course, for your arc length is going to be the theta in degrees multiplied by the radius. And sorry, it's not theta in degrees. This would actually be in radians. So in summary, the formula for the arc length in yellow over here is going to be used when degrees is given. So I'm going to write degrees is given. And then the formula highlighted in pink here is going to be used when radians is given. So if your angle measure is in radians, then use the formula in pink. And if the angle is in degrees, use the formula in yellow here. And it goes without saying that this theta here would be in radians. So for this question, we're asked to determine the length of the arc in the angle pi over 6 and the radius 13 centimeters here. So since the angle in radians is given, we can just jump right to this formula where A is equal to, and it'll be pi over 6 multiplied by the radius, we're going to say 13 centimeters. And when we plug that into our calculator, we get the following. Arc length would be about 6.8 centimeters in size. So over here it says a 40-inch pendulum swings to an angle of 18 degrees. So what I'm going to do is I'm going to draw this here. We got a pendulum like so. Okay, that is 40 inches. And then the angle that it swings to from, the axis of origin. In physics, you would call this the equilibrium position, but that angle here would be 18 degrees. Find the length of the arc in inches through which the tip of the pendulum swings. So one thing is the length of the pendulum. Okay, and I'm going to write this down to the side. The length of pendulum in any kind of questions like these is going to equal to the radius of a circle, because if you swing the pendulum all the way around, like if I keep it going like this, we can see that that is actually the radius. Okay, so that is going to be equal to the radius always. So what we could say is that since, again, we're asking for the arc length, but this time it's given in degrees, we're going to use the arc length formula in yellow here, where it's going to be 2 pi r 18 degrees over 360 degrees. And then when I sub in everything here, 2 pi, 40 inches, 18 degrees over 360 degrees, we end up with, and you plug this on your calculator, 12.57 inches. An arc of a circle is 1/6 of the circumference. Determine the size of the angle to the nearest hundredth of a radian, of course, that would form that arc. So remember that we have the ratio at the beginning of the video that A over 2 pi r is going to be equal to theta over 2 pi. So if I know that this is equal to 1/6 of the circumference, then I can just do the following. So I substitute 1/6 of the circumference in for A, and then I simply can just isolate. So that ends up being 1/6, since the 2 pi r's cancel out, over theta 2 pi. And then what we want to do is isolate for theta. So we're going to multiply both sides by 2 pi. And finally, that would give us 2 pi over 6 equals theta, and then simplified, of course, would just be pi over 3.